to provide it for people who are taking it online. And I'll share the screen. Hopefully it will come out. And our chapter today is the chapter on global climatic variation and energy reuse. There is no doubt that climatic variation is affecting our development of different forms of energy. I feel personally that our future is going to be a combination of the renewables as well as nuclear processes, whether it's fission and fusion or a hybrid of the two. The reason is that I worry more about the depletion of fossil fuels. Fossil fuels are a result of energy from our star, the sun, that has been stored over 200 million years. And within a span of 200 years, we are using it up. And in the process, we are destroying the fish tank that you are living in terms of the atmosphere of the Earth. So it's becoming a very interesting topic, climatic research. And you know that last week there was a meeting about the topic. So it's a topic of the hour right now. And I was talking to the gentleman here about the filters that humanity is facing in terms of continuing the technological civilization. I identified the possibility of an astral impact, an asteroid ending up our civilization. I identified gain of function research, which disguises the process of biological warfare as research on bioengineering and creating viruses that are more virulent than they are in nature. We identified global war, and one of the possible filters that our technological civilization has to go through is definitely the process of climatic variation. The topic generates very heated debates because there are different opinions, and we must be aware of these different opinions because it affects our livelihood in general. A few years ago, the process was designated as global climatic heating. And then came some people and objected to the term heating, and it became global climatic cooling. So is it heating or is it cooling? And what is the contribution of humans to it? Some people deny that humans have any contribution to the process and suggest that it is in fact more like a natural process that comes in from the relationship between our sun and our earth in general. So in that case, the title of our chapter here is not climatic heating or climatic cooling. It is climatic variation and in fact change. And we'll see what are the factors that people consider. And then I would like you to learn something that my own teachers taught me in high school. In fact, now we are in college, that to learn about the topic, you read the different perspectives, you study them maybe, and then forget them all and make your own opinion. And that is the way to learn about the topic. So I invite you today to listen to the different perspectives about climatic variation and change, forget the whole thing, and be smart enough to make your own opinion. So basically, it is increasingly realized that climatic variation and change, that's the terminology I'm using today, is considered as called the defining issue of the century. And it is no more an expected event into the future. It is already currently occurring, and we are living through it. And it's basically a part of the Earth's dynamic kind of nature. It is not a static nature. What existed on the Earth 1,000 or 1,000,000 years ago is not what exists today. It is a fact that climatic change is affecting our world. For instance, we know for sure that the massive sea ice in Greenland is covered with ice. Greenland, by the way, is owned by Denmark. And our late President Trump tried to buy Greenland from Denmark, and he offended them big time. But they're covered with ice. The Arctic is not land, it's open ocean. And we know for sure that ice is melting. So we are under the situation, even though it's very cold outside today, we are average-wise involved in a heating type of a process in general. You'll find that this has been monitored by American nuclear submarines that would go to the North Pole and simply surface. They would go through the ice, and year after year, they've been measuring the thickness of the ice, and the ice is basically getting thinner and thinner. The goal of people who do the research in climatic change suggests that there is a 40% chance that at least one of the next 5 years will be 1.5 degrees Celsius, which is about 2.7 degrees Fahrenheit. The temperature of the Earth would be higher than pre-industrial times. And the goal is not to go beyond that 1.5 degrees Celsius. And however, we are invariably headed there. So what today, I would like to show you some of our own research that suggests that if heating increases, then we'll find that the intensity of weather phenomena is going to be increasing. And I present you with a very, very simple heat conduction model. No supercomputers were used whatsoever as an example on how we can make such a prediction. Then we'll go from there into suggesting, okay, what if global climatic change goes beyond our expectations, and suggest basically like among other suggestions, a way of mitigating the effects and returning the whole Earth to a time where we had very temperate and nice climate. And in that case, we'll use nuclear processes. And I'll describe to you what I mean by that. This is our own research again. The Intergovernmental Panel on Climate Change, that's a United Nations group, reported that the 3 main gases blamed for global warming are, well, it's not just CO2, it's also methane. And methane is produced, of course, in marsh areas when organic matter decays. Some people suggest that it's also produced from the stomachs of cows, and they suggest that we shouldn't eat meat. And nitrous oxides is N2O, which is a laughing gas. The dentists used to basically anesthetize patients in the past by having some smell that N2O or nitrous oxide. It's a laughing gas. It makes you laugh and so on, but it will also anesthetize them. So they think that these 3 gases considered as gases that cause, of course, global climatic change are at the highest level in at least about 800,000 years. And an increase of 2 degrees Celsius is expected by the end of the present century. And we'd like to see what would be the effect and if there is any way of mitigating those consequences. There is here an introduction that's quite long, but I would like to come to our own research eventually and making a case that neither process anthropogenically, like effect by man, is 100% cause of global climatic change. Neither the only process that comes from the relationship between or the interaction between the Earth and our star, the sun. And that shows here by the temperature of the Earth over large interglacial cycles over the last 450,000 years. How do we get that information? They went into Antarctica. You know that Antarctica is land, but covered with ice. In some parts of Antarctica, the ice is 2.5 miles thick. They got core of ice And that ice accumulated over, well, the 450,000 years. Then they measure the concentration of oxygen 17 in that case in the ice, and in parts per 1,000. They call it in French, not percent. The percent is per cent in French, 100s, but per mil is 1,000. And they were able to deduce that at different geological ages, in millions of years ago, the temperature of the Earth indeed has varied. It varied from a level of 12 degrees Celsius average, that's a cool period, all the way to 22 degrees Celsius in warm periods. For instance, the Cambrian, yeah, that's a Cambrian age, and also Devon, the Earth was very warm. And then they observe in the ice that suddenly the temperature of the Earth cooled down, then it went up again, cooled down, went up again, and Jurassic area, that's the era of the very famous dinosaurs, Jurassic Park, the movie, if you watched it, it came down, then it warmed again and cooled, and we are here warming back again. So this is over millions of years ago, 370 million years ago. If we go to more recent periods, the glacial cores show that the Earth went through interglacial and glacial period. Glacial here means that there was glaze or ice, or in that case, it's ice translated into ice. The cores from those, obviously, if you think about the millions of years, that would be in measurements in ores of uranium and the half-life of different radioactive isotopes. But this one comes in simply for 150,000 years ago in the past. It comes from those glacial cores or ice cores that have been brought in from the ice shelf in Antarctica, as well as the Greenland and the North, in the area of the North Pole. 450,000 years ago, the average temperature of the Earth in degrees Fahrenheit was 20 degrees. And then it went through an interglacial period. It warmed up. Then suddenly the temperature went down, then it increased again. Suddenly it went down, increased again. Suddenly it came down, increased again. Suddenly came down. And we are basically a succession of glacial periods where the temperature in Fahrenheit is about 20 degrees Fahrenheit, and warming periods where the temperature of the Earth reaches 40 degrees. And obviously, 450,000 years ago, humans were not there, right? We date back on the Earth's surface only as humans, as primates, maybe at most 2 million years or even 200,000 years only. So it definitely, the Earth has been into periods of warming and periods of cooling. And that is a fact of life. And the humans were not the cause of these coolings. Now, if you look at the recent history of the Earth, we have exited from the last glacial period, like this area where we are living here now could have been under 50 feet of ice when the little ice age existed, maybe here. The temperature of the Earth was 11 degrees Celsius average. And then these are the years before present in thousands of years. 5,000 years ago, the Earth's climate started warming and then cooled, then warmed again. And this is what the people who do research in climatic research call it the Holocene climate optimum. The Earth's life on Earth was optimal when it was warm, as a matter of fact, during the Holocene optimum. During the Roman Empire, you'll find that the Earth was also in a warm period, and it was preceded by a cool period. Human migration occurred here in the range of about 2,000 years ago only. So we are really a young civilization or a young life form populating the Earth. And the medieval warm period, at least medieval in Europe and the rest of the world, India, China, Japan, and so on, you find that it warmed up, and basically the European continent prospered at that time. But then it came a little ice age about 500 to 600 years ago. And right now we are in, luckily for us, in fact, into a warm period. Again, before the Holocene, before the Roman Empire and the China Empire, India Empire, Japanese Empire, Middle Eastern empires, there were no humans to be affecting the climate. And when humans affect the climate, it's named as anthropogenic kind of effects. In 1816, in terms of variation of the Earth's climate, you find that it is named as the year without summer. The temperature is documented to have decreased very much. And this has been attributed to eruption of volcanoes on Earth. So that in that case, it's volcanoes. Volcanoes, of course, throw up into the air millions of cubic kilometers, in fact, of ash. And that dust in the atmosphere shades the Earth from solar radiation. So it results in a cold and dark climate. So the year without the summer in 1816 basically was a cold year that affected our historians writing it about in Europe in general. Climatic variations cause a feedback effect that when it happens, you find either positive feedbacks or negative feedbacks. We have cycles that control the climate on the Earth. Two of them are very well known and very, very well documented. These are short-term cycles. They happen from year to year. El Nino is in Spanish, the Niño is the baby boy. And it refers to Jesus Christ, of course, born supposedly around the beginning of the year. And it happens around Christmas time. That's why it's called the little baby. You'll find that the waters around the coast of South America, the western coast of South America, become warmer. And as they become warmer, less nutrients come to the surface. And the peoples in countries like Peru, for instance, or Chile, the fishermen there do not get enough of a crop of anchovies. Anchovies there is like corn here, is being fed to animal as animal feed. The opposite of it is La Nina. That's in Spanish also, the little girl. And La Nina is a climatic variation that is the opposite of El Nino. In that case, the waters in the Eastern Pacific around South America becomes cold. There is an upwell of the water from the bottom of the ocean filled with nutrients, and the anchovies catch becomes very good, and the fishermen there are very happy, and we can detect effects on the weather and the climate from these variations in general. So here is La Nina in terms of its occurrence. The waters become cool around South America, and it affects here North America too. You'll find that you get a Pacific jet stream changes its path and gives us a very cold climate in our area. Those variations are very, very well documented, and you notice here that the temperature of the continents, the North American continent in that case, during La Nina, it is cool. So La Nina causes oceanic cooling, whereas El Nino causes variations that are warmer. So here we can tell already that the Earth is subject to cycles. The Earth is a dynamic kind of an object in space, a beautiful little pearl on which life has emerged in our universe. The other short-term period, of course, we are all familiar with the seasons in general. And the seasons are coming from the fact that as the Earth rotates around the sun, and this is not to scale, in terms of volume, the Earth is a little tiny little pebble rotating around the star, the sun, 1/1,000,000th the volume of the sun. You'll find that because the rotation of the Earth is tilted by 23.5 degrees, around the vertical axis here, we get the seasons. Here we are getting into the winter, then comes the spring, then comes the summer, and then comes the winter again. It has to do with the exposure of the surface of the Earth in the angular, in fact, ways at the equator of the Earth, or the different events of the solstice around June 21st, the solstice of December 21st, and then the two equinoxes happen around March 21st and September 23rd. The sun radiation hits the Earth, and if it hits it in a perpendicular way, then what we call the solar flux, power flux, watts per meter squared, is harder here than it comes close to the pole. So it's larger in magnitude. So you find heating here during, say, the summer, or heating during the winter. And by December 21st, we find that this would be the coolest time of the seasons in general. There are other variations that affect the Earth's climate. Another one is the North Atlantic Oscillation. It's designated as NAO. Paleontologists are the people who study these variations in the climate of the Earth. And as I suggested, there was, it is affected, in fact, by the solar cycle. The sun goes through a cycle of 11 years. And over 11-year period, the poles, the magnetic poles of the sun revert from north to south and south to north. So as you revert on a cycle, you get a point where you have a zero. So when you get to that zero, the solar magnetic field becomes very low. And we observe that by not seeing enough sunspots. The sunspots, as we'll see later, describe really prominences in the magnetic field of the sun. And this means when we see lots of sunspots, that the sun is very active. It is at the peak of its cycle. We are emerging right now from a minimum in the solar cycle. And in that case, we don't have enough radiation hitting the Earth, but the cycle comes back again, and it varies in magnitude in general. How can we tell about those cycles? Well, scientists have been getting ice cores. One of the locations is what's called Lake Vostok ice cores in Antarctica. So Antarctica, as we know, is at the south part of the Earth. It may at one time be in a different location, maybe towards the north of the Earth, because they find there deposits of coal. So there were trees there at some point. But the ice cores are taken in an area called Lake Vostok, here shown here, where you have 2.2 miles thickness of ice. So imagine having all that thickness of ice deposited year after year after year after year, 450,000 years. Under it, because of the friction between the ice and the land there, you find that there is a lake. They call it Lake Vostok. And they sent their probes and found that there are very interesting forms of life that we don't have in our oceans. Basically, nature evolved there in a different way than what we have on the rest of the Earth. However, cores of ice taken from these 2.2 miles of thickness tell us about the variation of the climate of the Earth over the last 450,000 years. You can go for the fun of it yourself and become a climate scientist. You can get the data from references 1 and 2 here, like I did, and plot them for yourself and get a description of what the temperature of the Earth was in the last 450,000 years. So I got the data and I put it into the my Excel worksheet, as you could see here, and I plotted it. This is my own plot. And as far back as 450,000 years, you could see that you can plot the temperature variation in degrees Celsius over the period of 450,000 years. Notice here something interesting, that 400,000 years ago, the temperature was above the 0 by 2 degrees. And then it started going gradually lower and lower and lower and lower, and then jumped up. And then came down lower and lower and lower, and then jumped up. Lower and lower and lower, and then jumped up. Lower, 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 and then jumped up So the Earth has been subject to variation in different cycles. The first cycle shown here, if you look at the distance between the peaks, is 100,000 years. Okay, you can take that data and use some higher level of resolution, and you look at more recent times. So here is over the 50,000 years before present. Now notice here that when I put the data through the fitting algorithm in Excel, it shows us something interesting. It shows us that over the last 450,000 years, the linear kind of interpolation tells us that the overall temperature of the Earth has been coming down, little, very small variation down. It could be with our sun maybe becoming weaker, but there is no assurance that this is the case. If you take it though over only the last 50,000 years, you see the variation here again, and other cycles occurring. But when you come to the last 10,000 years, you could see that basically the linear curve fit goes up. So that's an indication definitely that our Earth over the last 50,000 years have been warming up. We are getting into a warming period. Now, if you go back and also generate more resolution in the data at that point and put it into your Excel worksheet, the data are from reference 3 and 4 in that case. So this is over 50,000 year period. You go and get it over the last, in that case, 0.5,000 years, which would be 500 years before present. And you could see that there are fluctuations because of the cycles, but in the last here, multiply that by 1,000, that makes it 200 years. Definitely, the temperature of the Earth is definitely increasing. There is no doubt about it from the ice cores. And this basically correlates with the advent of human civilization. So there is no doubt that yes, there are cycles that come from the interaction of our Earth with the sun. We have no control on this. But as humans, we are also affecting our climate. This sudden increase in the Earth's climate is designated by the scientists working on climatic variation as the hockey stick curve. It looks like a hockey stick here. And this is a determination then that is an effect that's anthropogenic, meaning that humans have interfered in our climate. So it is true that the climate variations depend on the interaction of our Earth with the star, our star, the sun. But it is also true that humans have had an effect, particularly in the last 200 years, which is the beginning of basically the industrial revolution in general. These ideas of different cycles affecting the Earth's climate have been introduced by a scientist called Milankovic. So he would be from the area of today's Serbia or Ukraine on Earth. And he suggested that the Earth goes through 3 different cycles. A cycle that he called the eccentricity cycle. These are variations in the Earth's orbital eccentricity. So if you think about the sun being here, that's obviously not to scale. If the sun is here, the Earth would be a very tiny dot right there. But you could see that the eccentricity of the orbit around the Earth around the sun is not a perfect circle. It has an eccentricity, and he suggests that that eccentricity is the one that causes the 100,000 year cycle that basically you are able to get if you plot the temperature data in Excel. He suggests that there is another cycle that comes in, and he called it the obliquity cycle. This is the changes in the obliquity of the Earth. Remember, we said the Earth has an obliquity here of 23.5 degrees that affects the season. And he calculated that this leads to a period of 4,100,000 years. And then he came up with a third cycle that suggests that the precision of the equinoxes cycles lead to another period of 19,000 to 23,000 years. And in that case, you have 3 cycles, and those 3 cycles interact with each other. Sometimes the cycles are constructive, so you get a higher values, and then they'll come down, but it is a superposition of 3 cycles. Here is a picture of our Mr. Milankovitch when he was young and when he is old. And in fact, this is being accepted as cycles that we are subject to, and we have no control on those cycles whatsoever. So what is the solution for human civilization? We basically have to adapt to those cycles. But when it comes to a cycle that we are creating ourselves as humans, and we can affect it, then of course we have to maybe be able to affect it in general. Here is the different eccentricity of the Earth's orbit around the sun. When the Earth is very close to the sun, it's named the perihelion. When it's far from the sun, because the Earth is rotating in an ellipse around the sun, we call it aphelion. And here is the cycles in millions of years. This is from a French source, so it's written in French. Cycle par million d'années, cycles per million years. And this is the density spectrum. You'll find that the 100,000 cycles happens 10 times per million years. The 41,000 cycles happen about 25 times per million years. There is a cycle 29,000 and 23,000 and another one 19,000. So you could see all those cycles now basically either create superpositions that can cancel each other if this one happens and the other one. So we are subject to cycle from the interaction of the sun with the Earth. In fact, the rotation of the sun of the Earth is not just not a circle, it's an ellipse, but in fact, both of them are moving together from the perspective of mechanics around the center of mass of the combination of the sun weight or mass and the Earth's mass. They both rotate around that little dot here that's closest to the sun than it is obviously to the Earth, because the sun has a much, much higher mass than the Earth. All right, other climatic variation drivers, of course, we can talk now about the role of CO2 in changing the atmosphere. CO2 is what, of course, you heard about, is a greenhouse gas. If we release it close to the Earth's surface, it traps the solar radiation, like rays, like glass, for instance, in your car would trap the heat over the summer inside the car, the greenhouse effect. However, the main processes that really affect us are the solar energy output. Maybe you have seen the solar flares that were discovered by that scientist here. That is, his name is Thomas Harriot, and he wrote essays, as you could see here, about the solar flares that occur in the sun. Some trivia that you'd like to learn about very easily here is that if you look at the solar flares, they occur in pairs. This is, for those early scientists, may have been a curiosity, but we know what causes them right now. So you could see here one pair of solar spots, a pair, a pair, a pair, a pair. And the reason for this, I'll explain it in a moment, comes in from the fact that the magnetic field of the sun, where charged particles, hydrogen and carbon and all the gases that constitute the solar mass in general, rotate around the magnetic field lines, and the magnetic field lines of the sun act like rubber bands. So near the surface, you'll find out of the corona, which is the area where most of the energy of the sun is being produced on the surface, near the surface, you'll find that the magnetic field lines have a south pole and a north pole. So they go up and down. And the reason we see the solar flares in pairs is the point where the magnetic field leaves the surface of the Earth and then returns back to the surface of the Earth. Other people scientists have observed this relationship between the sun when the sun is very active. Galileo, in fact, Galilei invented, of course, our telescope. He's shown here holding a telescope, and he was able to watch again the solar flares. And again, the sun is a very active kind of star, and the magnetic field is very complex in its structure. As I said, the magnetic field flips around and reaches a 0 point every 11 years. So this is the 11-year cycle of the sun. But look here, this is the origin of those two pairs of spots that very few people really know about. But the reason they are a pair is that the magnetic field acts like a rubber band. It exits from one point and returns back to the solar surface from another point. This again shows that idea here, the point where the magnetic field exits the surface of the sun and the one that it comes back. This would be a north pole. The south pole shows as a pair of sun spots. And again, as I suggested, the sun affects the climate on Earth because it flips. The magnetic field of the Earth simply flips. The North Pole becomes South Pole, and the South Pole becomes North Pole. And if you have any variation, a cycle, you find the point that you have 0. And this would be the minimum of the solar cycle in general. This is an actual picture of those solar flares, where you could see here the magnetic field of the Earth. This is the surface of the sun. This would be the corona. And you could see the magnetic field lines clearly forming a North Pole and a South Pole. And you know that charged particles rotate around the magnetic field lines. This displays here the fact that the magnetic field of the Earth reverses, and that affects the climate here on Earth. In that when the magnetic field reverses at one point, it reaches a 0 value. So basically, we're not affected on the Earth by the magnetic field of the sun. The magnetic field of the sun reaches the Earth, and in that case, it shields the Earth against cosmic radiation. And if you are shielded against cosmic radiation, you'll find that the climate is affected because cosmic radiation acts as a nucleation sites for the formation of maybe raindrops or ice drops. So when the cosmic radiation from the sun is very powerful, those cosmic rays do not reach the Earth. So it becomes like the climate becomes drier. There is no nucleation of ice crystals or rain crystals around the cosmic radiation. So in that case, we have an 11-year, but in fact, it is 22 years. So the cycle to go up and down, reach 0, and then go back at the bottom in general. So there is a relationship between cosmic rays and the Earth, the intensity of radiation from the Earth. And years where the sun is very active, you could see here the sunspots frequency is very high. You notice immediately when you have lots, the sun is very active, 11-year here, another 11-year here, that's 22 years. You find that the cosmic radiation reaching the Earth is here a minimum. The magnetic field of the Earth shields the Earth against cosmic radiation, and you end up maybe with a situation where no rain, no ice storms occur, as when the magnetic field of the Earth is very low, so more of cosmic rays reach the surface of the Earth. I talk more here about the relationship of cosmic radiation and the solar spots. This is another diagram that documents that they are negatively correlated. So the solar constant, which is the number of watts impingent on a meter square on the Earth, sometimes is when at the top of the solar cycle here, you'll find that the cosmic radiation reaching the Earth is very low. And when the solar spots or the solar constant is low, more cosmic radiation reach the Earth, and definitely it affects our climate on Earth. And I had experiments, in fact, on particle accelerators in general. Cosmic radiation interacts with the atmosphere of the Earth, the nitrogen in the atmosphere, here nitrogen-14. The cosmic radiation produces neutrons. It ends up producing isotopes of helium-4, beryllium-10, and when it interacts with oxygen-16, I wrote the equations on how basically the composition of the atmosphere can be quite varied with the interaction of cosmic radiation with the surface of the Earth. This is a topic that you can try to use for research. We started monitoring and keeping track of solar variations in general around the year 1750. And so far, we have been monitoring the solar flares or the activity of the sun for 25 cycles, 250 years or 260 years in that case. And you could see here that it varies. This is the year 2000 data, and it goes to a minimum and then increases. But the size or the magnitude of the solar flares varies from year to year. You could see here that this is a very weak cycle of the sun, sunspot number, but here it would be a high number, and it has to do with the magnetic field of the sun. So we have had, in fact, 400 years of sunspot observations shown right here, and there are names given to them. When the sun activity was very low, we got a mini ice age, particularly in Europe, because that's where it was observed. And this is named the Maunder minimum and the activity of the sun. It became lower again around the year 1800. It is named the Dalton minimum. It had another minimum around 1900. They gave it the name Glassberg minimum. Here we are within a modern maximum. And there is basically a prediction that, oh, it is not that you are getting to global warming. Look at this prediction here. They're predicting that the solar constant or the sunspots will reach a minimum around 2050, and they call this the modern minimum. That the suggestion is that by the year 2050, we may get a mini ice age. So we are not talking here only about global warming. We are talking even about global cooling. And the debate goes on and on and on in terms of the effect of solar radiation and the relationship between the sun affecting the Earth's climate. So this is one typical year here from the 2020 up to now we are 2022 here. You could see that the solar activity increased and then came down, and we are back again into a cycle where the solar activity is going up, and with the effect that can happen on the Earth's climate. We are right now re-entering in 2022, cycle 25. It's named 25 from the time that we started observing solar radiation. The point I'm trying to make is that we are at the mercy of our star, the sun. This is a picture of the sun that is not active. If it is not active, you get basically minimum irradiation. When it is active, you could see here the solar flares happening in basically in minimums. And some people, the NASA prediction for the solar cycle, SC stands for solar cycle 25, by 2025, they think it's going to be cooler than the previous solar cycles. And basically, we have to adapt with it, and adapt to it and use it. And this is not pie in the sky, really. Very, very big science is being done. This is the SOHO satellite. I think here S stands for solar. I don't remember the rest of it, but this basically is a solar, it is a satellite observing the observation from the sun. And all the data, by the way, is available to the minimum in general. Let us look very quickly on what happened during the Maunder minimum. It's not pie in the sky. These are pictures in the city of London. That is the Thames River. And you could see here that people went there with on ice skating. In that picture here is a painting, actually, having fun on the ice. But obviously Europe at that time was into a mini ice age. There is no doubt about it. Some people suggest that that little ice age occurred because of volcanic eruptions. When volcanoes erupt, they send their dust into the atmosphere, and that contributes, other than just also adding sulfur dioxide as a gas, apparently sulfur dioxide will cool the climate in opposition to the CO2. So the CO2 and the methane and the nitrogen oxide heat the Earth's surface, but the sulfur dioxide and the dust from volcanoes shield the Earth's surface, and you end up with cooler weather in general. The ultraviolet from the sun also affect the atmosphere. This is a picture taken of the sun. Again, you could see the solar flares here in the ultraviolet region of the electromagnetic spectrum. Okay, so let us become a little mathematical here. How much is it that radiation reaches the Earth? This is described in climatic research by what I call the Mayer's radiative forcing formula. And some people call it the climate sensitivity. It describes the infrared forcing. The word forcing basically is the power flux. So the units would be watts per meter squared. The climate scientists use the word forcing, but in fact it is power flux. And the suggestion is a formula on how the CO2 is contributing to the infrared forcing. Infrared, of course, means heat. In the electromagnetic spectrum, we have the visible spectrum, ROGBF, the colors of the in the white part of the spectrum. Above the red, you find the infrared, and we sense infrared by our skin. It's heat. So in that case, you take 5.35 as an empirical value, multiplied into the natural logarithm of whatever ending CO2 concentration divided by the starting CO2 concentration. So the ratio of increase in the CO2 concentration, the logarithm of the ratio is what is designated as the infrared forcing. So suppose that we double the CO2 concentration in our Earth's climate. That formula suggests that it is now 5.35 multiplied into the natural logarithm of 2. The natural logarithm of 2 is 0.693. So you end up with 3.71 watts per meter squared if you double the concentration of CO2 in the atmosphere. Now, if you go and do not control the CO2 emissions, the radiative capture equation tells us now that the log 2 becomes the log of 4, and if you quadruple the CO2 concentration, you end up with a natural logarithm of 400 parts per million divided by the existing 280 million. And in that case, the energy from the sun, the forcing becomes 1.91 watts per meter squared. This was at the beginning of the Industrial Revolution. And that suggests, in fact, here that this suggests if you take 1.91 watts per meter squared divided into 3.71 watts per meter squared, you'll find that it is half the forcings towards the CO2 doubling from the pre-industrial age level already has been realized in our existing time. And if you use the Intergovernmental Panel on Climate Change estimate of the temperature increase over the same period, they calculate that it is an increase in the temperature of the Earth from the doubling of CO2 concentration of 0.6 degrees Celsius. But notice the error bar here. It's plus or minus 0.2. It could be on a normal distribution 0.4, or it could be 0.8 in that case. So basically, we are in a situation where it could be dimming, or meaning that our sun would decrease the intensity of radiation, so the Earth would cool, and it could be warming depending on the cycles that come to us from nature. We cannot ignore this, and this is the graph that I'll describe and then stop at that for today. This is what's called the radiation forcings. It is a graph from the Intergovernmental Panel on Climatic Change, IPCC. You can read more on their website. And I show us here what they call the forcings in units of watts per meter square. This is M-2 here, that's watts, or power flux, in fact. And they show us here that the CO2 contributes this amount of about 1.6 watts per centimeter cube, with an error bar here up or down. Methane also has a contribution that is positive to the heating of the Earth, as well as halocarbons that are used in air conditioning in cars or homes. So that's why they're being banned. And you get forcing from the ozone in the troposphere. The troposphere, as we'll see later, is a region of the Earth where the weather phenomena are being created. But it is not only positive forcings or positive contribution that increase the temperature of the Earth. There are contributions that decrease the temperature of the Earth, like surface albedo. Albedo means the reflection of the solar radiation, aerosols or pollution in the air, dust. The solar irradiance is very small, but if you add the positive values again and subtract the negative value, the net result, anthropogenic, meaning caused by humans, is what is shown here at the bottom of the graph. And we cannot ignore this. However, the debate is very rambunctious, I would say, because of that very large error bar. So the conclusion of our lecture today is that it is true that humans have affected the Earth's climate, and maybe we have control on it, but there are other processes that we only have to adapt to. We cannot control the reactions that happen in our star, the sun. I'll ask you to read and watch a PowerPoint presentation and write us a summary about it.